Okay, Assalamualaikum all and good night. So this beam is a continuous beam A, B, C, D. So D is far end pin. D is far end pin. C and B is internal support. A is fixed, far end fixed, far end fixed. So moment and applied moment at B clockwise, UDL on member CD is 150 kilonewton per meter. Okay, we will start with the first step. Step 1. Step 1, we have to calculate stiffness factor K. It is small k, small k. Okay, there are 3 members. So we have member AB. So KAB. So for KAB, we will use 4EI because far N is referring to A. For N is referring to A, so we use 4EI over L. So this is 4EI. We divide by L is 2.8. So it is equal to 4 divided by 2.8. 4EI over L. So 1 point, it is 1.429. 429. This is for AB, member AB. Next one is K for BC. K for BC, internal, BC. Both are internal support, so we use 4 also. It is 4 EI divided by 3. And this is equal to 1.333 EI. Because EI will be cancelled when we calculate distribution factor. And for member CD, so D will be the far end. C is internal. We don't call internal. We when we're talking about far end condition, it referring to the last point, the end point. So D is the end point. D is far end pin. So for far end pin, we use 3 EI over L. 3 and it is 2 EI. So 3 times 2 EI divided by 3. 3 times 2. It is 3 EI over L. So CD is 2 EI. So 3 times 2 divided by L. So it is 2 EI. Okay, this is for stiffness factor as the first step for moment distribution method. Okay, move to step number 2. Step number 2, we have to calculate distribution factor. Distribution factor. Okay, the symbol is DF. We will use distribution factor to calculate and moment, to distribute moment. Okay, so distribution factor, look at the end point, the N A and ND. Distribution factor for N fixed. N fixed is, for N fixed A is 0. For N pin D is 1. So distribution factor. Okay, distribution factor for NA, AB. This is equal to K divided by total K. But for N fixed, it is divided by infinity. So the F for NA, AB is 0. This is because of fixed N. distribution factor for BA. Next is distribution factor for BA. For BA, it is DF. DF. BA. What is DF BA? To calculate distribution factor, it is K divided by total K. KBA, KBA divided by KB. Distribution factor DFBA is KBA divided by KB. So this is KBA divided by KB. KB come from BA plus BC. Sorry. Yes, BA plus BC. KBA. B here. BA, we have BA and BC. And KBC. Means KBA per KB. KB is stiffness factor for joint. KBC. B, we have BA and BC. So, this one, BC. So, what is KBA? KBA is equal to KAB. What is KBC? We get from this. This is KBC. KBC is also same with KCB. KAB is also same with KBA. It is the same member. It is the same member. So for KBA, we use KAB. KAB. So it is 1.429. 1.429. KBA equal with KAB. It is the same member. So it is 1.429. We divide by total. BABC. So it is 1.429. We plus by 1.333. So this is equal to 1.429 plus 1.333. We get 0.517. 0.517. Okay, this is how we calculate distribution factor for BA. So distribution factor, the formula is K for member divided by K for joint. K for member. Which member? For member AB, but we want at NB, BA. KBA divided by KB. The FBA means KBA divided by KB. KBA is 1.429. We get from KAB here because it is the same member. We have to divide by KB. B is actually BA and BC. BA and BC. So it is 1.429 divided by 1.433. Okay, next after this is KBC. DFBC. Not K. DF. Next is distribution factor DFBC. DFBC is equal to 1 minus 0.517 because B at joint B, we have BA and BC. We have BA and BC. So once we get BA, DFBA, we will get DFBC from 1 minus DFBA. So it is 1 minus 0.517 because distribution factor at joint. Distribution factor at joint equal to 1 except fixed end. So we get 0.4248483. So this is equal to 0.483. 0.483. This is distribution factor for member BC. For BC. Okay, next is distribution factor for CB. Distribution factor DF for CB. And for DFCB, it is KCB divided by KC. It is KCB divided by KC. It is KCB divide by KC, and C is CB and CD. K is KC is KCB and KCD. So this is KCB and KCD. It's KCD. So this we will get KCB is equal to KBC. It is the same member. KBC, KCB is the same. KCB, KBC is the same. So we get 1.333. This is 1.333. We divide by 1.333 KCB, and KCD is 2. So this one is equal to 1.333 divided by 3.333. We got 0.4. So once we get this as 0.4, so DFCD is equal to 0.6. 0.6 because this is at the same joint, CB and CD at same joint. It is equivalent to 1. Okay. So this is the second step. This is the second step, calculate distribution factor. This is the first step, calculate stiffness factor. Okay. So that is why the importance of knowing how many N here. How many N here? We have 3 members. We have 3 members. We have member A, B, and AB has 2 N. BC has another 2 N. CD, we have another 2 N. Member N moment referring to all these 6 N moment. So this is MAB, MBA, MBC, MCB, MCD, MDC. So this N moment produce 6 distribution factor. Distribution factor start from DFAB, DFBA, DFBC, DFCB, DFCD, DFDC. So that is why here we have 6 DF. AB, BA, BC, CB, CD, and last one is DFDC. So this one is DFDC. And DFDC, since it is KDC divided by KD, that's the formula. This one is KDC. And KDC is KCD. It is the same. It is the same. And divide by and we divide by KD. KDC divided by KD. And KD from this, since it is the last point, so at joint D, it is only 1. DC only. There is no DE. So that's why when we divide by the same, because this is KD, because this should be KD, and there is no DE. So it is just KDC. So that's why we get DFDC equivalent to 1. We get this equivalent to 1. And this is for N pin. And actually all join. The DF, the distribution factor is 1. Distribution factor is 1. Distribution factor is 1. Except fixed N. Distribution factor. Except fixed N because KA because KA is infinity. That is why the FAB, the F at fixed end is 0. Because fixed end is actually not the end of the structure. Because normally when we analyze one beam, that's not represent the real. The real may be more than A. It is infinity. Cantilever end is the end of structure. Roller is the end of structure. Pin is the end of structure. Fixed, not the end of structure. Fixed end is infinity. So please remember, distribution factor for fixed end must be 0. Distribution factor for end pin must be 1. Okay, so there are 6 distribution factor we get from 6n. We get from 6n here. 6n. Okay, so next step is step number 3. We have to determine the moment. The first member and moment in the table. We use moment distribution method. We used moment distribution method to calculate member and moment. It is moment. And fixed and moment is the first member and moment in the table. So we have to calculate fixed and moment. And fixed and moment is behavior. And because of the member cannot carry load, it has to be divide to the support, the joint, the nodes. So fixed and moment means we have to distribute the loading to nodes, to join. And we have to distribute it equivalently, just like what we have done previously in stiffness method. Means that whichever member that has loading on top of it, member that is subjected by loading, means that AB has no FEM. AB has no FEM. BC has no FEM. CD has FEM because of UDL. The moment, the applied moment 125 kilonewton meter subjected at joint B is not FEM because FEM is member with load. FEM is member with vertical force on the member. FEM means UDL on the member. FEM means triangular load on the member. And moment at B is not FEM, it is joint moment. Okay, so we can only get FEM from member CD. Fixed end moment. Okay, so we get from member CD. So it is FEM CD and FEM DC. FEM CD and FEM CD is negative. I have explained in class, I have explained in previous video, FEM due to loading one negative, one positive. Because of the behavior, we compare with sign convention. It is negative WL squared over 12. It is 150. Is W. L is 3 over 12. So it is 112.5. This is 112.5 kilonewton meter. And the other one is FEM DC, ND. Okay, when we calculate FEM, we can have this assumption, assume both end fixed. Even though in the real structure D is spin, Okay, we can start by assuming both n is fixed to calculate fixed n moment. So both n fixed means both have moment. So we will have fixed n FEM DC. This is DC. So this is positive. One negative, one positive, 112.5 kilonewton meter. Okay, this is the third step. Okay, next step is the table. Next step. Step 4. We will distribute moment. We will distribute moment. This is the table, distribution table, where we will distribute and carry over the moment. And finally, we will total all the moment in the table, and it gives us the member and moment distribution table. Okay, for the table, I want to move to this Excel. Okay, so it has AB, BA, BC, CB, CD, DC. 6N. DF, 0 here. Zero 0.517, and 0.483, and then 0.4, and then 0.6, and then 1. That's for distribution factor. And then FEM, fixed end moment. Okay, fixed end moment. Fixed end moment. Fixed end moment. Okay. For CD, for CD, it is negative 112.5 and positive 112.5. Okay, this is 112.5, 112.5 negative, 112.5, and 112.5 positive. Okay, remember the moment that we distribute is joint moment. That is why we change sign. We change sign because FEM is member and moment. FEM is the first moment in the table, and it is member and moment. But remember, we distribute joint moment. I have explained this in the lecture video last week. The process is we distribute joint moment. And joint moment is opposite with member and moment. Fixed and moment is member and moment. That is why we have to change sign. Okay, now because the beam has joint moment. The beam has joint moment. So what should we do with this 1 to 5 clockwise? What should we do with this 1 to 5 kilonewton clockwise? We have to distribute this. We have to distribute this 1 to 5 to BA and BC. But we do not have to change sign because it is already joint moment. It is already joint moment. So distribution is here. We have joint moment. We have joint moment at B. we have joint moment at B. It is 1 to 5. It is 1 to 5 positive, clockwise, 1 to 5. This is joint moment. So for joint moment, we don't have to change sign because it is already joint moment. But for CD, for CB and CD, joint moment at C means C is combination of CB and CD. C is combination of CB and CD. When we combine this 0 and negative 112.5, we get negative 112.5. But we have to change sign to translate this to joint moment. So joint moment for C. Joint moment for C is positive 112.5. Okay, another one. This one. Another one. This. What should we do for this? Because of distribution factor is 1. Because distribution factor is 1, means at distribution we will distribute it. So FEM is 112.5. Opposite with that is negative. Joint moment is negative 112.5. This is joint moment at D. Joint moment at D. This is joint moment 1 to 5. This is joint moment 1 to 5. We get directly from the diagram. It is 1 to 5 and applied moment subjected at joint B. So it is joint moment for B. So that's why I put at the center of BA and BC. It is not come from fixed end moment. It is already joint moment. So we don't have to change sign. Okay? So 112.5 is joint moment at C. We get from fixed end moment. That is why it is positive. Fixed end moment is member end moment. It is 112.5 and it is positive. And for joint D, we get the joint moment from FEM. So it is opposite. It is negative 112.5. Okay. Then only we distribute. Because this step, I put additional this, okay, into this example because of the joint moment 1 to 5 that is subjected at point B. So next, we will start with the first distribution. You have to remember the process. The process is, it is joint moment times distribution factor. Joint moment times distribution factor. This is 0. Okay, for BA, it is joint moment times distribution factor. It is 64.625 because it is already joint moment. Joint moment times distribution factor. Joint moment times distribution factor. Okay. For CB and CD, positive 112.5 is now joint moment. So we just need to times this with 0.4, the factor, the distribution factor. So we get 45 and another one 112.5 times the factor. And distribution factor for DC, because it is 1. it is 1. So distribution here is joint moment times with the factor. And normally without joint moment in the question, we do not show this in the table. That's why when we put the answer, we change sign. Okay? So this is distribution. After distribution is carry over. After distribution is carry over. In carry over, we have two factors. Carry over factors, we have two. We have 0.5 and we have 0. 0.5 and 0. And 0, the 0 carry over factor will only be used for N, ND, or N roller. And for carry over, we will carry the value. We carry the value to opposite join. Means AB, we have to carry A to B, we have to carry B to A. BC means we have to carry from B to C, from C to B. For CD, we have to carry from C to D, from D to C. And since A is fixed, B and C are internal, D is pin and it is the end point. So C to D, the factor is 0. For C to D, the factor is 0. So I just put here the factor 0. And I want to highlight using different color and small letter, small font. Okay, this is the 0 factor. The rest is 0.5. The rest is 0.5 for AB, from B to A, 0.5, the factor. This is all internal, we use 0.5. That's why we divide by 2. Actually, you don't have to write this. This is just to guide you, okay, the factor. And actually, you don't have to write in the table. Okay, this is the factor. The factor. For ND, because ND is pin, the factor is 0. The rest all 0.5. Okay, we have to carry the value to opposite. Carry the value to opposite. 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 This is 0. Because the factor is 0. So, for carryover factor from B to A, it is 64.625. We divide by 2. It is 0.5. Okay? So, next. This one. We divide by 2. This one. We divide this by 2. Okay, this one we get from D to C. We divide by 2. But this one, the factor is 0. The rest, the factor is 0.5, but not for D and D, the factor is 0. That's why we get 0. Okay. Then we just continue as usual, continue distribution, and then continue carry over. So we do not need to put any more this line for joint moment, because after this, we just need to change sign as usual. Okay. So distribution here for BA and BC. So it is positive here. So distribution, we have to change sign. Distribution, we have to change sign. That's why I put negative. Okay, so it is 22.5. Actually, the process is like this. It is 0 plus 22.5. We have to time with the factor, distribution factor. Okay, so we get negative 11.6. So this one, negative. Negative because we have to change to join moment. That's why we put negative here. Okay, so total moment means 0 and 22.5. That is the total moment at joint B. We have to time with the factors, distribution factor for BC. Okay, and these four values, the total must be 0. Because MB is equal to 0 and it representing the pin support. Okay, these two. Okay, negative for joint moment, it is CB plus CD joint moment times with the factor 0.4. Okay, and for CD, negative for joint moment, total moment is CB and CD times with factor 0.6 times with the factor 0.6. We get 15.6. We get 15.6. Okay, and then there's no more here for DC. Okay, we just continue the carryover. Okay, we have to continue. And actually we have set the formula here. We have set the formula here. We have set formula. Okay, that's why I do this in Excel because I can copy this. Okay, so now I get the carryover. So all divide by 2. Okay, there's no more here. And actually we don't have to put 0. The moment 0, we don't have to write. Okay, just leave it blank. Okay, then distribution. Okay, we just need to repeat the process again. Total moment, change sign to get joint moment and time is distribution factor. Okay, so I copy this formula for second, third distribution. Okay, and then this is the carryover. And then distribution again. Okay, you have to do it manually. 5 or 6 time distribution. This is carryover. This is distribution. Distribution 1, distribution 2, distribution 3, distribution 4. But now it's carryover. Okay, next is distribution. Okay, another one. Okay, stop must be at distribution, not carryover. Distribution. If this is carryover, then you have to continue with the last distribution. Zero point zero something, then stop. Normally, we stop at 0.0 something. Okay, this is the last distribution. Okay, now the end moment. Okay, so total, we total all the moment, excluding joint moment this line. Okay, we don't include this, excluding this. Okay, total start from FEM. This is 0, so we will start from this. The total is 24.8. 24.8. I want to change to 3 decimal places. Two, three. Okay. Okay, next. We start from 64.625. We have to total all this. Okay, I want to change to 3 decimal places. 3. It is 49.578. 49.578 here. Okay, next for BC, start from 60 until the last distribution. Okay, so I want to change decimal places here. Three, not 2, 3. It is 3. Okay. Okay, these two, MBA and MBC. MBA plus MBC. This is just for checking. We will get back 125. 125, which is equivalent to this. This total. Without joint moment 125, we will get 1 negative, 1 positive. But with an applied moment subjected at point B, so the total of MBA and M is CB. Next is CB start from 45. Start from 45, we total this. So it is 81.4. 81.4. Okay. Then start from this, yeah, not this one. Start from this. But for CD, we have to start from this. Negative 112.5. Plus this and continue. Okay, so total this first. And don't forget, we have to plus with this answer. We have to plus with the other one here. See, we get same value, opposite sign, because MC at pin, MC is equal to 0. Okay, 3 decimal places. Three. Okay, and for D, okay, just ignore this line, yeah. So in total, it is this one and this and this, and we get 0. This one and this, we get 0. Okay, so this is the table. This is the table. Okay, so this is the end moment. And this is without support settlement. This is just due to loading only. This is just due to loading only. Okay, so let's say from this, I want to continue to draw the shear force diagram and bending moment diagram. Of course, in order to determine the shear force diagram, we have to start with using, we have to use the moment from the table to complete the shear force diagram. And after that, we will draw the bending moment diagram. We can highlight all the salient point because we get bending moment diagram from shear force diagram for the salient point. Okay. We want to draw shear force diagram. Step number 5. Step 5. Analyze. No, not analyze. Draw. Shear force diagram. And to draw shear force diagram, we have to start with, okay, we will do it one by one member. We will start with member AB first. For member AB. Okay, this is for member AB. This is step number 5. Okay, for member AB. Okay, so what we need to do is we have to draw the free body diagram of each element. So that is why the importance for you to understand the what is the meaning of end moment, where is the location. Okay, beside member end moment. Okay, beside member end moment, what else? Okay, so this is the beam. When we resolve this into member, it is not only member. It is combination of member and joint. It is combination of member and joint. And this is just for this member, the free body diagram is just showing the member and moment. And actually beside member and moment, it has here AY and BY, 1 for the shear value because it is support, right? At A is support, at B is support. Okay, there is no loading on member AB. So this is actually MAB. This is MBA. Okay, this is the free body diagram. Okay, and then in between B, AB and BC, it has joint here. This is joint B. So at joint B, the 125 is actually here, 125. This is 125. Moment at joint B. Okay, so this is actually BY. So what is BY? BY is BY1 and BY2. BY is at joint directly. So when we draw the element, the member, for member AB, it has BY1. For member BC, it has BY2. So what is BY? BY is BY1 plus BY2. Okay. For member BC, so we have here MBC and MCB. So at C also, it has the vertical reaction. This is C. So this is CY1. And between BC and CD, here is the joint C. Okay, so at this joint, it has CY. And CY is CY1 plus CY2. This joint C. Okay, for member CD, this is MCD, this is MDC, and on the member, it has UDL. 150. This is 150. At D, it is pin. Okay, even though it is pin, but we just need to count the vertical force, because as far as we concern, we have learned this in stiffness method as well. The horizontal force, horizontal displacement can be neglected. So we don't need to count it, even though this is pin support. So it behaves just like roller. Okay, this is dy. This is actually what happened when we resolve this. When we resolve this, means that if we want to draw shear force diagram, we have to analyze element by element, member by member. Okay, so now we take member AB, the free body diagram of member AB. This one. Member AB, MAB. Okay, member AB, it has MAB, MBA. Okay, the assumption made is this is MAB, this is MBA. It is the sign convention, but we need to refer to the diagram. If the moment in the table is negative, means that we have to change sign. In this case, both are positive. So remain the sign. So it is 24. This is 24.803 and 49.578. And don't forget, we have to put here AY, this is BY1. AY and BY1 means the shear force. Okay, so when we analyze this, we just need to analyze. It is just like we analyze simply supported beam. So how we analyze simply supported beam? If this is A and B, this is A, this is B. B. Okay, it take moment at one end. It is 24.803 plus 49.578. Moment at A, 2.8 meter. So it is minus 2.8 BY1. So BY1 is equal to 24.803 plus 49.578. We divide by 2.8. Because we want to calculate this value and this value. There is no intersection, there is no point load. Okay, it is just the shear value. It is 26.565. 26.565 kilonewton. So what is A? AY. So if you want to write incomplete, of course, you have to apply total Fy. But we already know, right, what is the AY value. Okay, so how we determine that? Total Fy. So it is AY plus BY1 equal to 0, right? So AY, we get negative 26.565. So one negative, one positive. So for the shear force, it is, negative. Remember the diagram. The diagram start at 0, end at 0. Okay, AY is negative means in the diagram, this one is negative. Five, six, five. 565. BY is positive. 26.565. Look at the arrow. Okay, we just need to follow the arrow. Start from 0, means the point is here, below line. So when we draw ke bawah, downward. Okay? And it is just straight line until this point, and we follow the arrow to close loop. And we identify the sign for beam, for this beam AB, from the arrow shown. Because this arrow will push this one to rotate counterclockwise. So this one is negative. Okay, so this is negative. This is the shear force for AB. This is A, this is B. Okay, for member BC, member AB, member BC. Okay, we just need to repeat the same. Member BC. Member BC, it is BY2 and CY1. Okay, it is like this, MBC, MCB, but look at the table. Okay, look at the table. And again, this is positive, positive. So remain sign. 75.42 and 81.40. 81.403 75.422. 75.422. The distance is 3 meter. There is no point load. There is no UDL for member BC. Okay, we have to calculate this and this using equilibrium equation. And actually, you don't have to show. I just want to know the value. Okay, so when taking moment at B, it is 75.422 plus 81.403 total. We divide by 3. So we get CY1 equivalent to 50,275. And we get this in opposite sign, 52.275. So for the shear force diagram, okay, it is down and up. What does it mean? So this is the first value going down. Okay, this is the last value going up. Okay, this is negative because from this and this, it rotate clockwise, it rotate counterclockwise, so it is negative. Okay, so this is the shear force diagram. The value is 52. This is 52.275 kilonewton along 3 meter length. Same with this. This is 2.8 meter and the value is 26.565 kilonewton for shear force diagram. The shear force diagram for AB. Okay, what about member CD? Member CD. Member CD, UDL. This is CY2 dy moment original. Before we start any analysis, at the beginning of the process, we assume that this is the sign convention. But the value, we must refer to the table. The value is negative and 0. The value is negative and 0. Negative means we have to change sign. Here, the value means the value is negative and it is 80, 81.403. 81.403 and this has no value. UDL. $150 and 3 meter. 150 kilonewton per meter, 3 meter. And we have to calculate CY2 dy, the shear value. Okay, so as usual, just like we analyze simply supported beam, so we take moment at C is equal to 0. It is now negative 81.403. Okay, we have to plus with 150 times 3 times 1.5 minus 3 dy. This is equal to 0. So dy. So dy we get 150 times 3 times 1.5. We minus by 81.403. We divide by 3. 197.866. 197.866 kilonewton. This is dy. So for CY2, it is actually 150 times 3. 450. We minus by 197.866. 252,134. 252,134. So with this value, okay, CY2, 252.134. dy, 197.866. UDL, 153 meter. Moment, 81.403. So how the shear force diagram look like? Okay. Start with 0. Arrow like this, right? So this is the point. We have to draw upward. Draw upward. Okay. And the last point, the end point is 197. We have to draw like this. Means this is the point. Draw and join this. This is straight line. Okay. So this is positive. This is negative. The value is 252.132 and 197.866. And now we have to identify the distance because intersection. There is an intersection means ada maximum moment kat sini. Maximum moment at intersection of shear force diagram. Maximum moment at intersection of shear force diagram. And we will determine this maximum moment in the bending moment diagram using the area of shear force diagram. So means that we have to calculate the area of this triangular. We have to have this and this. Okay, how to get that? Okay, it is force divided by moment, not divided by W. It is force, kilonewton. It is kilonewton divided by kilonewton per meter. So we get meter. So kilonewton here is 252.132. That is in kilonewton. 252.132. It is in kilonewton. We divide by W. W is 150. So we get 1.68. So this is 1.68 meter. So if this is 1.68 meter, the other one is 3 minus 1.68. We get 1.32. This is 1.32. Or you can also calculate by using 197.866 divided by 150. 1.32. It is the same. Total must be 3. Okay. So that's the shear force diagram for each member. Member BC, member CD. Okay. Then step number, this is step number 5. Step number 6. We have to draw the bending moment diagram, BMD. Bending moment diagram. Okay. Have AB, BC, and CD. Okay, the moment that we get from table is positive, 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 negative, 0. Means that in the diagram, okay, where is the point? Start with 0. The second point is here. We just need to refer to this. And then this is the last point. Okay, this one. We just need to refer to the arrow. And then we just need to join the dot. Join the dot. This is the BMD for member AB. Positive, negative. The value is the value in the table, 24.8 and 49.6. 24.8, 49.6. Okay. Next one, BC. The first point is 0. And then look at the arrow above line. Look at the arrow below line. This is the end point. Okay, join this dot. This is the BMD. This is positive. This is negative. What is the value? What is the value? 75.42. 75.4. 75.4. Of course, you can draw point to just put higher to represent 75.4. $75.4 and 81. $81. 81.4. Okay, and the last member, it is member CD. Member CD, okay, at point C, this is the point. This is the first point. Then the second point. The last point is 0, but it has intersection. Intersection. We get something like this. This is the maximum moment. The maximum moment. So this is positive. This is negative. Okay, so what is this value? What is this value? Okay, so it is actually just like this. Okay, for the shear force, this is just for member CD. This is just for member CD. So for member CD, the shear force, this one. Okay, so this is C. Okay, the intersection, this is D. Okay, now we are going to draw the BMD. Okay, the value is 252132. 2521 or 1. 197.9. 197.9. 1.68. 1.68 meter and 1.32 meter. This is positive. This is negative. For the moment, it is 81.4. 81.4. And it is negative. So this 81.4, we have to plus the area of shear force diagram. It is negative 81.4. Okay, this is negative 81.4. We have to plus the area of the first triangular. We have to plus 0.5 times with 252.1 times 252.1 times 1.68. We get the value is equivalent to 130. It is positive 130.4. 130.4. And we have to minus the second triangular. So this 130.4, we minus the area of second triangular. 1.32, 197.9. Okay? Seems like 0 point something, 0.2. So because of the just decimal places, it is 0. Okay, so the curve, the bending moment, okay, so this is actually shear force diagram for member CD, and this is bending moment diagram. Okay, shear force diagram and bending moment diagram for member CD. Because member CD has intersection, we determine from shear force diagram. This is how we analyze. And actually, when we analyze shear force diagram for member AB and member BC, okay, without shear force diagram for member AB and member BC, also we can draw the bending moment diagram because there is no maximum moment. Okay, it is just, okay, I have shown here, it is just how to analyze the shear in, okay, in this beam using MDM. We use end moment value to determine the shear value. This is how we determine, okay, for member BC as well, and for members CD because of UDL. So please remember, for UDL we have to analyze whether it has maximum moment or not, because sometimes we may not get this type of shear force diagram. We get trapezium. When we get trapezium, means there is no maximum moment. Maximum moment only occur when there is an intersection in the diagram. Okay, so if we want to analyze this member CD only separately, so we will do like this. Just focus on member CD because member AB and member CD does not get any effect. Okay, so just focus on this. So this is the salient point. Okay, that's all. Thank you very much. So this is how we analyze member this beam. Okay, considering only external loading. Okay, in the next session, in the next video, I will continue to include the support settlement. So how we include support settlement in MDM, in moment distribution method. Okay, so for this example, careful with the joint moment that is given directly at joint B. This 125 will return because it will affect the distribution moment in the table in the first distribution. Okay, and then careful also with the end condition and pin, because normally students seems forget to include the far end condition when analyze MDM, when analyze any beam or frame using MDM. I normally found student who just use all 0.5, ignoring the end condition of the beam. So when we have like this beam, N is roller, N is pin, careful with K, because K for N pin and roller is 3 EI over L, and careful with carryover factor because the factor is not 0.5, it is 0. Other than that, it is the same. Okay, so this is how we analyze. Start with the first step, the second step, okay, the third step, fixed end moment, the table, and normally the question will end with diagrams. Okay, that's all. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor.
Thank you, Doctor.
Sadam, thank you, Doctor.
Thank you, Madam.
Thank you, Doctor.